This is part 4 of our video tutorial on gas laws. In the last video tutorial, we were looking at the ideal gas law, which is a combination of the combined gas law and the Avogadro's law combined together to create PV equals nRT. We are also introduced to the universal gas constant, which is 8.314 kilopascal liters per mole Kelvin. So let's see a problem where we actually use the ideal gas law. So let's try and solve this sample question. First of all, let's write down our givens. I have a 2.7 liter balloon, therefore my volume is equal to 2.7 liters. Now since I don't see the word volume anywhere else and it doesn't say that the volume is changing, I don't have to say V1. It's just one volume, that's it. Next, I know it's filled with oxygen gas at a pressure of 105 kilopascals. So my pressure is equal to 105 kilopascals. And a temperature of 292.30 kelvins. So my temperature is 292.30 kelvins. My question is, what is the mass of oxygen gas? So oxygen gas is diatomic, so it's O2. So what is the mass of my oxygen gas present in my balloon? So my approach, well, I know I can't use the combined gas law because I don't have two pressures, I don't have two volumes, don't have two temperatures. I only have one set, so how can I solve for it? So obviously I can't use that equation. So I'm going to start working backwards. I'm looking for the mass of my oxygen gas. So mass, the only equation I have for mass is mole times the molar mass. Now I do have the molar mass of oxygen. I just have to look on the periodic table. And I find that 16 grams per mole. But since I have two oxygens, because it's O2, it's diatomic, it's going to be 16 times 2 grams per mole. And then I got to multiply that by the number of moles. But I don't have the number of moles. It's not given to me. So what's the only equation we have that has moles in it and volume, pressure, and temperature? The ideal gas. PV nRT. So if I rearrange the equation algebraically to look for N, it becomes PV divided by RT is equal to the number of moles. And once I solve for this, I can plug it into this equation over here. So let's start plugging stuff in. Pressure, in this case, is 105 kilopascal. Volume is 2.7 liters. R is my universal gas constant, and I automatically know it. It's 8.314, or 8 pi, because I've memorized that number. And the temperature is 292.30 kelvins, which equals the number of moles. So if I solve for all this, number of moles is equal to 0.116 mole. So having this number over here, I can now plug the information in to here and finally solve for my answer, which equals to 3.71 grams of oxygen gas. So that pretty much does it for the gases and atmospheric chemistry unit. Let's just do a quick recap of our unit. We first started off doing some background information. We looked at the particle theory of matter and the kinetic molecular theory. And we looked at how it's used to explain the behavior of gases. We then talked about the ideal gas and the assumptions we make in order to help us simplify our calculations. And then we took a look at the idea of pressure versus force versus area, and how pressure is related to force and area, whereas force is independent. And then we talked about how atmospheres, kilopascals, millimeters of mercury, and torricellis were all related to each other. There are different methods or different units of measuring pressure, and how to convert back and forth between the two by setting up our ratios. We then looked at the idea of how to convert to the Kelvin scale, and why we prefer to use the Kelvin scale, how to convert from Celsius to kelvins. And then we looked at Boyle's law, Charles' law, and Guy-Lussac's law, and how the three of them can be combined to create the combined gas law. Next we looked at Dalton's law of partial pressure, and how it's not really an equation per se, but more of a concept to be used to solve or help you to solve certain problems. We looked at the first part of Dalton's law, where the total pressure is equal to the individual pressures inside. And then the second part to Dalton's law was that the volume, the percentage of the gas that it's made up of, is directly proportional to the partial pressure of that gas. So if nitrogen makes up 50% by volume, then it should be 50% of the total pressure as well. Then we looked at Avogadro's law, which allowed us to relate volume to moles as long as the temperature and pressure remain constant. Then we looked at the idea of standard temperature and pressure, STP. So anytime you see this acronym STP, you automatically know what the temperature is and what the pressure is. And then again, the magic number 22.4 liters per mole, which is the molar volume of any gas, any ideal gas at regular STP, is going to be 22.4 liters per mole. Finally, we combine the combined gas law with the Avogadro's law to create their ideal gas law, which introduced the topic of the universal gas constant, which is experimentally derived. But if you ever forget this number, you can always solve for it by solving the ideal gas law at STP. And that's it.